Okay, 11.3 is about what is called the dot product of two vectors. The dot product is found or is denoted with an actual dot in between the vectors. There's more than one type of multiplication with vectors, so we do need to specify. So for finding the dot product, we multiply all of the corresponding component values of the two vectors and we add them together. So this does give us just a single quantity. This is a scalar. Okay, the dot product is scalar, so in other words, we get a number, not a vector, as the dot product. Also, if there are only two components, like if we're only in 2 dimensions, then we just don't have this third part, or you can think of it as the last component in a 2-dimensional vector is always 0. All right, so page 567 has some properties. Please review these. It talks about which operations or how the dot product is closed under, like commutative property, distributive property, etc. So please review those. Okay, so first extension to the dot product that we need to know is how to find the angle between two vectors. All right, and if we find the dot product, that's the same thing as the product of the two magnitudes times the cosine of theta, which is the angle between the vector. And when I say the angle between the vector, what I mean by that is if we line up the two vectors with the same tail, then theta is this angle between them. Now, this is also an angle between them, but generally we're not talking about the reflex angle, but the acute angle. All right, so we're going to do an example here, finding the smallest angle or finding theta between these two vectors. So I'm going to find the dot product and the magnitudes of each vector, and then we will use this equation to solve for theta. All right, so first, the dot product is going to be 3 times 0, 0, plus negative 4 times 5 is negative 20, and then plus negative 1 times 2 is negative 2, so negative 22 is the dot product. And then for the magnitude of u, that's going to be the square root of 3 squared plus 4 squared plus 1 squared, so root 36. Nope, 26. Sorry, root 26. Okay, and then for the magnitude of v, that is root 0 plus 25 plus 4, so root 29. Okay, so then using this equation right here, actually I'm going to rearrange and say that cosine of theta is equal to the dot product, negative 22, over these two products. So root 26 times 29. So then to solve for theta, I'm going to do cosine inverse of this, and this is back in radians now. So that means that theta is approximately, what is it? 2.5 radians. Okay, so that is the angle between two vectors. Okay, now why do we care about this? Well, one thing that the angle between the two vectors can do is it can tell us whether the two vectors are parallel to each other or orthogonal to each other, which orthogonal is essentially the same as perpendicular. And for the first part, two vectors are orthogonal if the dot product is 0. And so if we think about this, if we think about, oh, hold on, it's not scrolling. There we go. Okay, so if we think about this equation right here, if two vectors are perpendicular to each other or orthogonal to each other, then that means the angle between them is pi over 2. And since cosine of pi over 2 is 0, and then the magnitude of vectors are not going to be 0, that means the dot product over here is going to be 0. So if the dot product is 0, then we know that the two vectors are orthogonal. Okay. And so let's look at this one. What must the angle be between two vectors so that the dot product is equal to plus or minus the product of the magnitudes? In other words, this means that because we know dot product is equal to the magnitude times cosine theta, that means that here we are saying cosine of theta is equal to plus or minus 1. Okay, so where is cosine of theta, either positive or negative 1? Well, that's going to happen at theta equals 0 or pi, or 2 pi, 3 pi, etc. But just between 0 and pi, we're just using those two. Okay. If the angle angle between them is 0 or pi, then that means we have parallel vectors. Okay, if two vectors are parallel, then the angle doesn't really exist. Like, okay, if I draw two parallel vectors, they would actually they could just sit right on top of each other, or one could be longer, or one could be going the other direction. Okay, so with the same starting point here, could be going the other direction, but those are parallel, and then the angle between them is, if we say between them, is either 0 or pi. Okay. All right, so looking at a couple pairs of vectors, we want to know the relationship between those vectors. So for this one right here, and this, remember, this is basis form. I is 1, 0, j is 0, 1, and then we can write it in component form if we would like as 2, -1, and -1/2, 1/4. Okay, so to determine if they are orthogonal, parallel, or neither, let's find the angle between them. Okay, so I'm going to start with the dot product. So U dot V is 2 times -1/2, which is -1, plus -1 times 1/4, which is -1/4, which is -5/4. Okay, so then for the magnitude of each, we have the square root of 4 plus 1, so √5, and then for V, square root of 1/4 plus 1/16, which is 5/16, 5/16, which is √5/4. Okay, and so then using our equation, cosine of theta is equal to the dot product divided by these two magnitudes. So -5/4 divided by √5 times √5/4, which is just, this is 5/4. -5/4 divided by +5/4 is -1. Therefore, these two vectors are parallel. Okay, go ahead and try part B, and then pause it, try part B, and then hit play, and then see if you get the same thing I do. Okay. All right, then over here for part B, label this one A. Again, we're going to do the dot product first. So, and I'm just going to call this A and B since they're not labeled. So A dot B is 6 times 2, so 12, and then plus -2 times 5, so -10, plus -1 times 2, so -2, which is 0. And because I did the dot product first, I don't actually have to check the magnitudes, because a dot product of 0 means that the two are orthogonal. Okay? All right, and so now we get to another application of the angle between two vectors, and that has to do with planes. The equation of a plane is represented as a linear function with 3 variables, so ax plus by plus cz equals d, okay, where a, b, c, and d are constants. So let's say that we have a vector with, oops, where'd they go? Stop doing that. Hold on. I don't know what's going on. Is that everything? Okay. So we have a vector that is represented in component form with ABC. Okay. And then we have a point that is a fixed point. That's going to be P sub 1 here is x1, y1, z1. This is not a vector. This is just a point in space. Okay, so the set of points, this is a general P. Notice the difference. This has subscripts 1 and this does not have any subscripts. So this is the set of all of the points that satisfy that the dot product of the vector from the fixed point to any point times or dot the vector is equal to 0. Okay, so just to kind of give you try and visualize this. So if we have some plane and we have a fixed point on a plane, that's P1, then every other point in any direction at any distance from here, all of these points would be P. So all of the points in the plane would just be the general point P. And if we draw a vector from the fixed point P1 to any of these, any point in the plane anywhere, if the dot product of that vector with vector n, let me draw a vector n here, is 0, so vector n is going to be something like this. So this will be n, and it's going to be, because the dot product is 0, remember that means orthogonal. So if this vector is perpendicular to all of these other vectors that we might draw, then that means it represents all of the points in the plane that are perpendicular to vector n passing through point P sub 1. Okay, so just to kind of say that again, all right, if we have a fixed point and a vector, okay, we can put the vector so that it has a tail at the fixed point in space, okay? And then vector n is orthogonal or perpendicular to every other point starting at P1 and going through this plane. That gives us we can use that to write the equation of a plane, okay? So let's go through this with general terms here. We can first write a component form of the vector starting at this fixed point and passing through any generic point, okay? So that's going to be, so the vector from P1, that's a 1, not a comma, to P in component form is going to be x minus x1, so just subtracting the components here, x minus x1, y minus y1, z minus z1, okay? And then the dot product of this times vector n, which again, times, I'm going to write it down here just so I can see them together, is just A, B, C. The dot product of those two is A times the quantity x minus x1 plus B times the quantity y minus y1 plus C times the quantity z minus z1. And because we are defining this as the plane that is perpendicular or orthogonal to vector n, then this dot product has to be equal to, 0. Fix that 0, okay? So how does this represent the equation of the plane? Well, then from here, we could just distribute our a, b, and c values and then move a times negative x1 plus b times negative y1 plus c times negative z1. We could just add that to both sides to get our constant over on d, just d to represent the constant on the other side, okay? All right, so let's go through an example of using this here. So we want to write the equation of the plane that passes through, this is our fixed point, and it is going to be perpendicular to vector n, which is also 2, negative 4, 3, okay? So the first thing I'm going to do is I'm going to write the vector that goes from the fixed point to any generic point x, y, z. So we'll call it P1 to P. And I know this says P here, but that's going to be P1 because it's fixed. So that's going to be x minus 1, and then y minus 2, and then z plus 3, okay? And then I'm going to do the dot product of this with vector n. So I'm just going to, instead of rewriting that, P1 to P dot n is, so then we have 2 times x minus 1, minus 4 times y minus 2, plus 3 times z plus 3, and then we know that this is equal to 0, and now I'm just going to distribute and rearrange. So we get 2x minus 2 minus 4y plus 8 plus 3z plus 9 equals 0, and then we've got 15 over on this side. I'm going to add that to the other side, so we get the equation of the plane is 2x minus 4y plus 3z equals negative 15. So that is the equation of the plane.